All right, everybody. Welcome back to physics. So I do have your tests graded and ready to hand back. I get them at the end of class, along with the reflection assignment, and I'll explain how the reflection assignment works. And it's an opportunity to gain back some of the points that you may have missed during the test. So worthwhile at this. There's an announcement. I'll make it now in case you have to leave early. I'm going to make it at the end of lecture in case people come in late. Next Monday, the instructor who is usually in here before us has asked to get a little bit extra time to administer a test. So I ask that you guys do not enter the classroom before 11:05 on Monday, and expect lecture to begin at 11:15 on Monday. It'll still end at 12:15. It'll just be a little bit shorter than usual. It'll be 15 minutes shorter than usual. But I just ask that you respect the students in the class before us and give them the space to have a little extra time on their exam. Sound good? All right, I'm going to make that announcement at the end of class as well, just in case people come in late. See, we are recording. We are good. So we're going to continue on with our physics topic, right? What were we talking about on Monday? Can somebody remind me? Interactions. We were talking about interactions, and we were talking about interactions because once you know the interactions, that are acting on any object, doesn't matter what the object is, you know the interactions acting on that object, and you have a description of that object. Well, once you have those two things, you can then make predictions about the motion of an object, right? So if you know the interactions, then you can figure out the motion, and this tells you a lot about the behavior of what that object will do. So you want to know the interactions to make predictions about the motion. Now, the motion of an object, of course, described by the position and displacement of an object, which are described by the velocity, which are described by the acceleration. And specifically, when we talk about interactions, what we are finding out about the motion is the acceleration. So the interactions tell you about the acceleration acting on an object. Now, for us to be able to do that, to make that conversion, we quantify our interactions. We give it a numerical value. And that quantification is done through the use of forces. The force acting on an object is just a way for us to give a numerical description to the interaction that is occurring. So for every interaction that we can define between two objects, we can find a numerical force associated with that interaction. And from that numerical force, we can determine the acceleration, which is a quantified value related to the motion of the object. So if we're talking about quantified values, we say force and acceleration, right? Force is related to acceleration. And how are those two things related? Well, they're related through Newton's laws of motion. And we've seen the first two laws of motion that say the force, and it's a vector force. This is going to be very important, especially as we move into today's lecture. Force is a vector, so we'll put a vector arrow atop it. So the vector force, F, is equal to the mass of an object times the vector acceleration. Again, acceleration has direction as well. And acceleration tells you about your object speeding up, slowing down, or even turning. So your vector force is equal to the scalar mass. Mass is a scalar. There's no directional component to mass, multiplied by the vector acceleration. So we have force is mass times acceleration. This encompasses Newton's first two laws. Remember, his first law says that if there is no force acting on an object, well, technically no net force, there is no net force acting on an object, then there is no acceleration. And that's clear here. If F is equal to 0, then A is equal to 0. Must be the case, because mass is non-zero. And then his second law is described with this equation that says the acceleration is proportional to the force. And what's the constant proportionality? Mass. So this tells you Newton's first and second laws. We haven't delved into his third law yet. We will at some point, but we're going to spend some time here studying these first two laws, the laws that describe the interactions and how interactions are related to motion. Feel okay so far? All right. So then we look at different interactions and we say, well, interactions are just pushes and pulls, right? And we've studied a couple of these so far. We've looked at the normal force, which describes the interaction of a surface supporting any object. And we use the word normal not because it's some regular force. No, we use the word normal force because mathematically, what normal means is perpendicular to the surface. So your normal force is always going to be perpendicular to the surface. If we look at a table, well, perpendicular is directly up, right? So that's the direction of the force. Again, direction matters. It's a vector. We looked at gravity. Well, gravity always pulls downward. Down. Direction is down. Direction matters, right? So we have this idea of directionality of forces. We went through some examples. We imagined a cat on the table. And we're going to continue on with this discussion of forces. But before I move forward, are we feeling all right about normal forces and gravitational forces? Roughly, okay. We're going to talk a little bit about tension forces today. This is going to be our example for a little while. Tension forces. Tension forces occur when the interaction is done through a rope. And these are exclusively going to be pull-type interactions. They pull on objects, right? If you have a rope, such as I have here, and I attach the rope to the table, there's no way I could push the table through the rope. Tension is always a pulling-type interaction. A pulling-type interaction that occurs through a rope or a wire or a string, something of that nature, right? So tension is a force that is through a rope, through a string, through a wire, and is almost always a pull-type interaction. Sound okay? All right, let's start off with a nice example. And for this example, I'm going to need 2 volunteers. Who wants to volunteer for me? All right, come on up, come on up. All right. What's your name?
Abram.
Abram. So we have Abram. You're going to be on the left-hand side of the classroom. Name?
Brian.
A-N-T?
Yes, sir.
Is that right?
Yes.
Cool. So what we are going to do here is look at a tension interaction through a fun game of tug of war. You go ahead and take one side. You go ahead and take the other side. And we are going to have a nice tug of war. Now, let's go ahead and pull tight, not pull yet. So we have a rope here. The object of interest is going to be this flag right here in the middle. That is what we care about. Now there's going to be 2 forces acting on this. There's going to be a force caused by Abram pulling to the left and a force by Bryant pulling to the right. Sound all right? Okay, let's go ahead. Let's pull tight. Let's have you come a little closer on the rope. Maybe grab from right here. Sound good. Maybe come a little bit closer too. Okay, right about there. Sound good. Let's try to not hurt each other.
Can I
You cannot. Typical tug of war game, grab has to be facing towards the wall. Now, we're going to do 2 rounds of this. We're going to do 2 rounds of this. The first round, I want it to be a tie. Okay? You guys think you can handle that? All right. Let's make the first round a tie. So we're going to go ahead, pull tight. All right, 3, 2, 1, go. Now, how do I know that Abram and Bryant are pulling with equal forces?
That's not moving.
It's not moving. Acceleration is 0. If acceleration is 0, that means the net force is 0. We're going to examine this on the board in a moment. But we have acceleration is 0, indicating that our 2 forces are equal in magnitude. Equal in magnitude. We're going to remember that equal in magnitude, but there's a crucial note about directionality that we'll talk about in a moment. Let's go ahead and let's do a game of tug of war. Let's actually both take a couple steps this way. There we go, there we go. Okay, let's play a game of tug of war. Ready?
I got a weak leg.
It's okay, it's okay.
Okay.
All right, let's go. Ready? 3, 2, 1, go. Oh. All right, we're seeing a little bit of movement this way. Okay, let's stop. Which force was larger, Abram or Brian? Abram. How do we know Abram's force was larger? It was moving this way. The acceleration is to the right, the larger force is to the, left. My right, your left. Larger force is to the left, larger acceleration is to the left. Okay, so what are we going to do? Well, we're going to give Bryant a little help here. Let me get a third person up here. Anybody. Third person, third volunteer. We will wait. All right, we got a volunteer. Come on up here. What's your name?
Daniel.
Oh,
Sorry.
sound good? All right. Sorry to do this. This is the cost of winning the first round. All right, everybody ready? We're going to examine the flag. We're going to see which way is the flag going. Let's take another step this way. I suspect I know which direction we're going. All right, ready? 3, 2, 1. Let's go ahead and go. All right, let's stop. Which way did the flag move? Which way was the acceleration? All right, which side had the larger force? Was it Abram or was it Bryant and Daniel? Absolutely. Okay, go take a seat. We'll probably return to this later. But we have enough information here to start a little bit of an analysis, right? We did 3 rounds. We did the first round in which it was a tie. And in that case, in round 1, we want to take a look at the flag. Now, the flag would have had two interactions acting on it. What are those two interactions? Well, you might be inclined to say it's the pole of Abram or the pole of Bryant. You might be tempted to say that, but I would say consider what the actual interactions were, what were connected to each other. It was the rope, and I'm going to divide the rope into rope right and the left side of the rope left. And I do that because when we consider interactions, you want to think about what is physically touching. Most interactions that occur are what we call contact interactions. They occur through the contact. So we want a way to represent this, and we say it is a contact between the rope and the flag. Remember, Bryant, he was not touching the flag at all, right? He was holding the rope, which was holding the flag. Abram was holding the rope, which was holding the flag, right? So we have these two interactions. And we say that they both interacted through the flag through a tension, right? So I'm going to call this T left and T right to represent tension on the left, which is the force caused by the interaction on the rope. Does this sound okay? So I'm making one of these interaction diagrams, and then we look at it and we say, well, on the left-hand side, we had Abram interacting with the rope, right? Abram was pulling on the rope, and he was pulling on it, and I'm just going to write that this was some force Fa. I'm going to use an arbitrary applied force here, because it is not really given a name. It is just him pulling on the rope, so we'll say it's some applied force on the rope. Does that sound good? We have Abram pulling the rope, which is pulling the flag. On the right-hand side, we have... Nope, not Daniel. Bryant pulling on the flag. Pulling on the rope. I'll use F subscript B for some applied force, FB. Doesn't matter what it is. So we have this sort of line of action. Now the flag is very light, especially considering the amount of force that Bryant and Abram were putting on the flag. The flag is very light, so that means that technically speaking, we would say everything is interacting with the entire Earth. That is true through gravity. Gravity is affecting everything. But since the flag is light, it has a small mass, And to find the force of gravity, we take the mass and multiply by acceleration due to gravity. Since the flag is light, very little mass, that means that this force is very small. It is small enough that we will neglect it in our calculations. We'll see what happens when we can't. We'll see very soon what happens when we now take into account tensions and gravity. But for right now, we are going to say gravitational force is weak on the flag because it is very light. We take a look at the flag. That is our object of interest. That's what we were studying the entire time, right? And in the case of the flag, we can draw a free body diagram. Our free body diagram is usually the next step. And sometimes we could skip directly to this step if we're comfortable. But we would draw a free body diagram, which would have the tension to the left, the tension to the right. And what I'll do here to just have a little bit of completeness, I'll put a very, very tiny little arrow here to represent the force of gravity, the weight acting on the object. But it's small, so I'll put a small arrow because we are going to neglect it. But we have the tension to the left and the tension to the right. This gives us an opportunity to apply Newton's laws. Newton's laws apply in the vertical direction and the horizontal direction. For every free body diagram, you can apply Newton's laws in each of the three Cartesianal directions, x, y, and z. Typically, we will deal with two dimensions in this class, x and y, but it does apply in the third dimension if you wanted to. And what we can say with Newton's laws, net force in the y direction is mass times acceleration in the y direction. F net in the x direction is mass times acceleration in the x direction. Where for the y direction, we take up to be positive, down to be negative, as is typical. And for the x direction, we take right to be positive, left to be negative, again, as is typical. All right. Does it seem okay so far, yeah? So when we take a look at this, we say tension to the, if we look at the vertical, right? We'll start with the vertical, why not? When we look at the vertical, we say the vertical direction, well, the net force is equal to 0 because we're saying the weight is basically 0. It's negligible. And what does that imply? Well, that implies the acceleration is also 0. And that makes sense. The flag wasn't accelerating up, wasn't accelerating down, it was staying flat horizontal, right? So we have this first understanding that vertical motion tells us vertical acceleration is 0, and that matches the observation that we made during these tug of wars. And then we take a look at the horizontal. Again, whenever we deal with motion problems, it's usually a good idea to separate vertical and horizontal. Right now it's easy because our forces are directly vertical, directly horizontal. We'll see in a moment where vectors come into play. For our horizontal motion, we look at the net force in the x direction. The net force in the x direction, remember, force is a vector, force has direction associated with it. So what we might write is that the tension to the left is given by a negative value. We do that because we typically take left to be negative. So whatever force, it was on my left, Abram, right? Abram was on my left. So the force by Abram would have been a negative value because it was to the left. To the right, we give a positive value. So Brian's force, we would have said is positive, or the tension caused by Brian. We would have said is positive because of the directionality. Does that sound good? And we would say that's mass times acceleration. Again, Newton's second law applies. in the vertical as well as the horizontal direction independently of each other, and you can apply it for every free body diagram that you draw. Any questions? You okay about this? Now we look at the different scenarios that we have, right? In scenario 1. In scenario 1, we think back to what was occurring. The flag was stationary. If the flag was stationary, what does that imply about the acceleration? 0. The acceleration must be equal to 0. That means we look at the equation minus TL plus TR. The tension to the left added to the tension to the right is equal to mass times 0 acceleration, which means your forces add up to 0, which means the forces are equal in magnitude, mathematically speaking. We take this idea of Newton's second law, match it up with the experiment we just did, and we can get to the result that our forces are equal in magnitude. But what can we say, because the forces, magnitude and direction, they're equal in magnitude, they're equal in strength, but what can we say about their direction? They're opposites. They're equal and they're opposite, and this leads them to cancel out. Typically, we might call this balanced forces. It's balanced. Balanced forces give you 0 acceleration. Balanced forces give you 0 acceleration, and we like to say when we have 0 acceleration from our balanced forces, our object is in equilibrium. And specifically, we call it mechanical equilibrium to indicate that it's coming from mechanical forces. There are other types of equilibriums, thermal equilibrium, electrical equilibrium. But in this case, we would call it mechanical equilibrium or just equilibrium for short. So our balanced forces lead to equilibrium. These are cases of Newton's first law. Acceleration is equal to 0. Does this seem okay? Do we feel all right about this? All right, and then we asked to have a tug of war where they were actually pulling their hardest, right? When we saw them pulling their hardest, this was scenario 2. And in scenario 2, we say tension to the left plus tension to the right is equal to mass times acceleration. And we think back to the different forces that were occurring, right? We had Abram pulling and Brian pulling. Who was pulling harder? Abram or Brian? Abram. So which was the larger tension? Tension left or tension right? Tension left. So what we can say is tension left must be greater than tension right in magnitude. Yes? If tension left is bigger than tension right, then what we would see is minus tension left plus tension right. The summation of these two values in scenario 2 will always come out to be negative because the negative value is larger than the positive value, yeah? So that tells us that tension left minus tension left plus tension right is always going to be a negative value. Always going to be a negative value, yeah? So if it's always a negative value, then that means acceleration must be contributing that negative. Mass can never be negative. You only have positive masses. So if your net force, your summation of your two tensions here, if those come out to be a negative, well, then that must mean acceleration is negative, which tells us exactly what we observed, that our acceleration was to the left. And what's interesting about this is that our net force and our acceleration shared the same direction. The net force, the combination of your two forces, and your acceleration, they share the same negative direction. So we get the acceleration and the net force sharing direction. And then we look at scenario 3. When we look at scenario 3, called Daniel down to help Bryant, and when that occurred, what changed? Well, when that occurred, we still have tension left and tension right. We still have the same two interactions acting on the rope, but now we have Daniel also pulling on the rope with some force caused by Daniel. This means that the tension going to the right must have been larger now than the tension going to the left. So we go back to Newton's second law. Net force, tension left plus negative tension left plus tension right, your net force, is equal to mass times acceleration. And now we have that the tension to the right is going to be larger than the tension to the left. And when this is the case, that tells us that our net force, tension left plus tension right, net force being the combination of the two forces, will be positive, will be larger than 0. Your mass is positive. Your net force is positive. What does that mean about the acceleration? The acceleration must also be positive. Your acceleration will always be positive if your net force is positive. And this tells us that the acceleration and the net force must always share direction. All right. But what's the use of doing all of this if we're not going to do quantified values, if we're not going to come up with a way to mathematically describe whatever this object is when it's moving, right? What's going to be the point? Well, we can start to understand this motion, these tensions, when we start to understand the causes of the tension. So what we will do is first take a look. I'm going to assign random numbers, but what we're going to do is take a look at the three-body diagram when we consider the object to be the rope. So what we will look at, perhaps, nope, I wanted to do left first because that only has one interaction. And I'll circle it in a different color. What we're going to do is look at the rope on the left-hand side. We're going to say that is our object. We're only looking at the left-hand side of the rope. That's what I care about. When we look at the tension on the left-hand side, we can look at when we look at the rope on the left-hand side, we can get an understanding of the tension. And how do we do that? Well, the free body diagram will have weight going downwards, but for an object like a rope, weight is negligible, so I'm going to exclude it. Weight is negligible because the rope's pretty light. It's not that heavy. All right, well, what other forces do we have here? We have a tension to the left. A tension left going to the right. We flip the direction. Now, this is going to be an interesting aside. We flip the direction. Why do we flip the direction? Well, when we think about Abram, right? Abram was holding the rope. Abram was experiencing the rope trying to pull him rightward, yes? He was standing right here. The rope was trying to go that way. So that means the rope was pulling him to the left. Or to the right. Sorry, I keep flipping my directions in my head because that's my left. But to the right. And then we have Abram pulling on the rope and pulling on the rope to the left. So we have Abram pulling on the rope to the left. And we'll take a look at scenario 1. in the case of scenario 1, we think about the rope, and the rope itself wasn't moving. Remember, scenario 1 was the tie game, the game that was a draw. Was the rope itself moving? No, so the acceleration of the rope is, which means that the net force is giving us balanced or unbalanced forces. Balanced, wonderful. So we have the rope being in balance, in equilibrium, telling us that the net force, which is mass times acceleration, we're going to take a little bit step further back and start using this lettering for net force. Net force is mass times acceleration. We just discovered that the net force is equal to 0 because it isn't balanced. And when this is the case, we can take a look at tension to the left minus for the force that was applied by Abram. And we know that that should equal 0. Well, what does that mean? That means the tension to the left is equal to the force caused by Abram. Seems easy enough. It's the same sort of analysis we just did, yeah? But this time we get a connection with the force done by Abram. Do we feel okay about this? Yeah? So what we are going to do is come back over here to the analysis we did on the flag on the rope. Does that sound good? We come back to the analysis we did on the flag of the rope, where we said that for the flag, right? This was for the rope. Moving over to the flag itself, we say net force is equal to 0. Again, that gave us tension right is equal to tension left. But wait, we just figured out something about tension left. Those two things must be equal to each other. We can, when we're analyzing the system, and we're analyzing a system like this interaction diagram gives us different systems, we can bridge these gaps as long as it's the same scenario, as long as nothing's changed here, right? For scenario 1, we can maintain the same scenario. And we can bridge the connection between these different systems. And we analyze the system in orange here that gave us the tension left is equal to the force applied by Abram. And we have the system of the flag, which gave us that the tension to the right is the tension to the left. What that tells us, tension of the right is equal to the force caused by Abram. Does that sound good? Any thoughts, any comments? Well, we can do the same exact thing for scenario 1, taking a look at Bryant's. And what that would tell us is that the tension to the right for scenario 1, when it was a tie, when it was to a draw, is equal to the force of Bryant. And that leads us to the force from Abram being equal to the force from Bryant. And you'll remember that when they came to tie, and I asked you which was larger, the force from Bryant, the force from Abram, and we said, well, it must be equal. This is mathematically how we know it must be equal. We mathematically proved that their forces applied must be equal. We did it through tension. All right. Now all of this is taking you through painfully, step by step, the mathematics to deal with these forces. Now oftentimes we can skip some of these steps, right? We intuitively knew that Abram's force was larger, smaller, equal to Bryant's force, right? We intuitively knew that. We can use our intuition here. Our intuition was right. We ended up with the result that their two forces must, without a doubt, be equal to each other. We can use our intuition, but there is a mathematical framework behind our intuition that we should know exists. Because in scenario 3, we could probably make a free body diagram. This is scenario 3. We could probably make a free body diagram without having to worry about the tensions, because we know immediately that Abram was pulling to the left, right? So we could just say, instead of dealing with tension to the left, tension to the right, we could say force of Abram to the left. And we know pulling to the right in scenario 3, well, that was a combination of Daniel and Bryant. So we can say to the right, force of Bryant, force of Daniel. So do we need to go through every step? No, not necessarily. Not necessarily. But know that there is a whole mathematical framework behind getting to this result. And if you don't trust your intuition, but you should, you can understand this probably, how this root value diagram comes across. But if you don't trust your intuition, there's a framework that you can use to follow. And what this would tell you, force of Bryant plus force of Daniel minus force of Abram, that is our net force. Abram being negative because he's to the left. So we have this net force that is a combination of each of our individual forces. And from here, if we knew the values, we can figure out the net force, set it equal to MA, figure out all this. Okay, are there any questions, any thoughts? We can make things a little bit more complicated here in a moment. But if we feel all right about this, we can move forward. Yeah? All right. So how do we make things more complicated? Well, we make things more complicated by starting to introduce angles. And I will do a brief reminder, a brief recap on vectors, right? Because once we start dealing with multiple dimensions, we really need to start understanding this idea of vectors, right? It's a scary word, involves a lot of trigonometry, but the convenient thing is that once you understand how the three trig functions affect vectors, well, it just becomes repetition at that point. All problems are very identical to each other. So with vectors, I say let's have some arbitrary vector on some x, y axis. I'll call this vector vector A. A vector has a magnitude, and the magnitude would be the length of the arrow. And it has some direction. The direction is given by the angle it makes. Typically we use with respect to the x-axis. Sound good? Now every single vector can be broken up. Every single vector, regardless of what type of vector it is. If it's a vector, it can be broken up into its individual components. Some x component, given by that green arrow, and what that tells you is how far to the left or right, how far horizontally does this vector go. And you have some vertical components, some y components. You have a vertical component that tells you how up and down is this vector. And what is true is that horizontal and vertical are always 90 degrees to each other. So we have a right triangle here that is created with our vectors. So with our vectors, they create some right triangle where we can say for any vector A, this is just a stand-in for any type of vector you might interact with. For any vector A, we can say it is composed of some x component, ax. I'll use green there because I use green to outline it in the drawing here, multiplied by I hat. And then we add to that some y component. We'll call that ay, j hat. For every vector, this is true. You can break it up into its individual components, and this is going to be necessary for us as we apply it to these two-dimensional problems. Our vectors here are going to be force vectors. So what we might say is for any arbitrary force vector, F, whatever that force is, for any arbitrary force vector F, we can see that as a combination of some x component of that force vector, how hard is it being pulled directly horizontally? And some y component Fy j. So you can describe its vertical force component. In other words, how hard is it being pulled upwards? So we have these two different components. Does that sound okay? We can see the sort of alignment here, right? Where we're just replacing arbitrary vector A with the physical vector of force. How do we find these values? Well, to find these values, you use your trig functions, right? And we can say that force, the x component of your force, well, that will be found by taking the magnitude of your force vector. I'm going to write it out in orange here for a reason. But you take the magnitude of your force vector and you multiply it by cosine of the angle that it makes with the x-axis, multiplied by cosine theta. So we find our x component. And what is the magnitude of our force? Well, again, the magnitude of your force is just how long is this arrow if we display it in sort of an xy coordinate system. Or in the case of forces, it's how strong is that force? How many newtons is that force? So we ask the question, how many newtons is that force? So if this force is 25 newtons, well, that's the magnitude of it. It's how strong is the pull overall. We say, well, what is the y component? The y component is going to be found pretty identically, just this time using the sine of the angle. And again, this is as long as your angle is measured with respect to the x-axis, meaning it's from the x-axis to the vector. If it's from the y-axis, then you have to use you have to swap your sines and cosines, but I just recommend getting used to referring things to the x-axis. And it is still going to be true that this follows Pythagorean's theorem, as all vectors do, which says the magnitude of the force is given by square root fx squared plus fy squared. Take the component squared. That'll tell you the magnitude of any force. Okay, any thoughts, comments, concerns? All right. Let's get 3 volunteers up here. I like doing things physically. Let's get 3 volunteers up here that are different than Daniel, Abram, and Bryant. 3 new volunteers. Come on up here. Come on up here. 3rd volunteer. Sure, come on up here. Now this one's going to be a little bit different. Hold on to there. Because now we are going to do things 2-dimensionally. Hold on here. Actually. Yeah. All right. Trinity? J or G? J.
You said it maybe after the J.
Good. John? Okay. We're going to look at this 2-dimensionally now. So what this is going to be a picture of is top down, right? So we're imagining camera up at the top, looking down. I'm going to ask that you two spread out a little bit more. So let's have you spread out. And what we have now is an angle that's being created here. So we look at this top down and we now have 2 dimensions to it. You're going to pull directly this way, and you guys are going to try and pull sort of backwards. Sound good? And we're going to do this sort of two-dimensional tug of war. We're going to still look at this flag, and we're going to see, does this flag move? And the goal, try not to pull too hard. You've got the table behind you. And we're going to see, how does this two-dimensional tug of war play out? Now I want you guys to try and pull along the rope's axis, right? Don't try and shift horizontally. Let's try and maintain this angle. Sound good? All right. Ready to go? 3, 2, 1. Let's go ahead and pull. Wonderful. So let me ask, what is the acceleration? 0. We have a tie game here. We have a tie game here, but I want to analyze this system to understand something about the motion, because there's something interesting going on here about these off-axis components. All right, you guys can relax for a second. So what's interesting about these off-axis components is that both Trinity and Evangelina, both of them are pulling with some degree of force going in the perpendicular direction. But we're not seeing movement in the perpendicular direction. That tells us that we are balanced in the perpendicular direction. And both of them, as well as John here, are pulling in this horizontal direction, meaning that there's some balancing happening in the horizontal direction. And I want to take a look at that behavior mathematically. Okay, thank you. So we're going to take a look at that behavior mathematically, and I wanted to give us sort of a physical view of what is going on here, so that when we're looking at this, we have a better idea of the motion. So we have our 3 volunteers. I'm going to represent our volunteers with these 3 dots. And we are going to draw out the rope. We're going to draw out the rope. Right at John's hand. I want to look at the rope right at John's hand. Well, what we can do is create a free body diagram that shows John pulling to the right, Trinity pulling up and to the left, and Evangelina pulling down into in the exact same directions that the ropes are seen. We have them pulling in the same exact direction. Now, whenever you create a free body diagram, you want to keep in mind that there are coordinate systems that are associated with your free body diagram, because this tells you about the directionality. We are going to have some x component, some y component. Now when we look at John, John is strictly in the x direction. I know I drew it kind of off of his arrow, his horizontal arrow, but he is strictly in the x direction. Whereas Trinity and Evangelina, they are in the horizontal and vertical direction. They are off axis, meaning that they both have, according to their forces, some x and y components. And that is dependent on the angle that they are making. Whatever angle that is that they're making with respect to the x. And you can find their x components by taking however strong they're pulling, multiplying it by the cosine of the angle. We can find the y component by multiplying by the sine of the angle. And let's go ahead and do just that. I'm going to make some assumptions here. I'm going to make the assumption that the force being pulled on the string by Trinity, I'm going to say that that force is going to be of magnitude. And I write it out as magnitude by excluding the arrow on top of the force. This is a typical way to describe magnitude. I could have drawn absolute value signs around the vector to indicate magnitude, But shorthand for magnitude would be vector without the arrow. I'm going to assign some strength to it. I'm going to say Trinity's force was 35 newtons. Newton is our unit of force. So we're saying Trinity pulling with 35 newtons. We're going to say force of Evangelina is going to be of that same 35 newtons. And we're going to say that they pulled with some angle of 30 degrees. I'm going to put a decimal point there to indicate 2 sig figs. We have a force at an angle of 30 degrees, which is about what we have. So we imagine the tug of war, and we imagine assigning some value of force to each of these. Let's pretend we measured out. This is the strength of the force. 35 newtons is a pretty reasonable assumption here. So we have a 35 newton force, given that they're all for both Evangelina and Trinity. Does this sound good? Now for both of these, we would want to take these off-axis forces and break them into their components. Whenever you are dealing with forces in 2 dimensions, first thing you should do is break them into their components. We'll first look at trinities. For trinities, we know that the force is being pulled vertically up and to the left, right? So I draw my coordinate system that says we have y direction, x direction. Here's the direction of Trinity's force at some 30-degree angle. Does this sound good? And we ask, well, what is going to be the vertical component? What is the vertical component of Trinity's force? I'm going to call that FTX. No, vertical is y. FTY, or vertical component of Trinity's force. What is that going to be? Well, you find the y component of Trinity's force by taking the magnitude of Trinity's force and multiplying it by the sine of the angle, theta. So you take 35 and multiply it by the sine of 30. When you take 35 and multiply by the sine of 30, what do you get? Break out your calculator. Make sure you're in degree mode. What do we get? 17.5. Excellent. So we have 17.5 newtons for being the y component of Trinity's force. And we would say that it's positive. After you break it into its component, you want to look at the direction. If it's upwards, you would say it's positive 17.5. We'll see for the x component something a little bit different happens. For the x component of Trinity's force, that is to say, how hard is Trinity pulling to the left? What is the y component? Well, you find that by doing the magnitude, force of Trinity times the cosine of theta. And you would find the strength of the force that Trinity is pulling horizontally. So let's go ahead, put in your calculator. 35 times the cosine of 30. What is that? 30.3. Is that what we got? 30.3 newtons. But there's an issue here. What's the issue? Can we spot it? What is that? It should be negative. Why should it be negative? It's going to the left. It's going in the negative direction. This should have been negative. If you're using cosine and sine, chances are you'll have to double check that you get the direction right and insert the negative or positives manually. You want to double check that. I'll show you a way that you can triple check your result momentarily, but you can get this value for Trinity's forces. Now, you analyze next the other off-axis force, right? This is just one of our two off-axis forces. We analyze the second off-axis force. This is Evangelina's. And for Evangelina, you have your coordinate system here, vertical, horizontal. Force coming off at some angle, 30 degrees. And you want to figure out the x and the y components. Well, you do the same exact thing. Force of Evangelina's y component is going to be force, the magnitude of it, multiplied by the sine of 30 degrees. And when you multiply that together again, you get 17.5 newtons. And you do the same thing with the x component. And you'll find that you get same result as before. You plug them in, you get the same numbers. But I've made a mistake. What was my mistake? The y needs to be negative instead of positive. The y needs to be negative instead of positive because we are pointing downwards. We have a negative y component. So we double check that our negatives are negatives and our positives are positives. Now we have our two off-axis forces here broken up into their two components. Once we have our off-axis forces broken into their components, we can actually, I'm just going to do this around this board. Once we have our off-axis forces broken into their components, we can take the time, and this is a very useful step, we can take the time to redraw our free body diagram. Because our free body diagram over here, well, yes, it is good, and this is an actual physical representation of what's going on. We can redraw our free body diagram to be more mathematically useful. And we can do that by utilizing the components of our forces. Where we have our free body diagram, this is the dot representing the rope right at John's hand. We say John is pulling to the right. We have Trinity pulling with some vertical force given by the y component. This is 17.5 newtons upwards. And Trinity is pulling to the left with 30.3 newtons in the leftward direction. And we can do this because the summation of these two forces, force Trinity y, force Trinity x, gives us the combined effect of the whole vector. So we can do this. We can break into components, and it's equivalent to look at the components. Mathematically, it's equivalent to look at the components rather than the full vector. We do the same thing with Evangelina. And at this point, we triple check our signs. We see Evangelina's y component's downward. That should be negative. And it is. Evangelina's x component is leftward. So that should be negative. And it is. Trinity's y component's upward. It should be positive. And it is. And Trinity's x component should be negative because it is leftwards. So we triple check our different components. And now what we've done is we've taken our two-dimensional problem, which describes Evangelina and Trinity's forces as being at some angle in 2 dimensions. We've taken our two-dimensional problem and we've now split it into a singular horizontal problem and a single vertical problem. We've taken our two-dimensional problem, our single two-dimensional problem, we've broken it up into two one-dimensional problems. And once we do this, we can apply Newton's law to this problem. And for the vertical, it tells us that the summation of force of Trinity's y component minus force of Evangelina's y component should equal mass times acceleration. But we noticed something about that flag. What did we notice about that flag? It was stationary. Being stationary means acceleration is 0, absolutely. Which means the magnitude of Trinity's y component should equal the magnitude of Evangelina's y component. What do you know? We see they're both 30.3 newtons in magnitude. That checks out. We look at the horizontal component. And when we look at the horizontal component, we see that the force of John being the positive minus the force of Trinity's x component minus the force of Evangelina's x component must equal mass times acceleration. This is the net force in the x direction. They must equal mass times acceleration. But again, we noticed something about that rope. What did we notice? What did we notice? Acceleration is 0. It didn't move. Its acceleration is 0. It didn't move. It's in equilibrium. The forces are balanced. The net force is equal to 0. Which means we can now discover that the force of John is equal to the summation of force of Trinity plus the force of Evangelina. And when we add those together, the x components, 30.3 newtons, 30.3 newtons, sums up to be 60.6 newtons. We figure out how strong John is pulling. And he's pulling a little bit stronger than Trinity and Evangelina are, right? Pulling a little bit stronger. And, it's a game of 2 against 1, so it's coming out to tie, so it must be the case. All right. Now, what have we done so far? What we've done so far when it comes to forces is we've looked at and we came up with this idea that is dictated by Newton's law, right? We brought out that cart and we saw that acceleration depends on how much force we apply and the mass of the object. Wonderful. We've then taken that idea and we said, well, what kind of interactions might we have and how do these interactions occur? And we come up with this one-dimensional case that we analyzed with the cat on the table and that sort of thing, right? Saw net force. And now we are expanding our idea of net force to include off-axis forces. Well, when you have an off-axis force, whenever you have an off-axis force, you can always break it down into its components. And when you break it down into its components, using trig, like any other vector, when you break it down into its components, our two-dimensional problem then becomes two one-dimensional problems. And our one-dimensional problems are solved with Newton's law. Do we feel okay about this? Any thoughts and comments? All right. With the time left, we are going to get our tests back. Some of us have already gotten it because we were in lab earlier today. And some of us are still waiting on it. Along with the tests, I am giving you this assignment to do this weekend. I want you to focus on it this weekend, and I want you to take it seriously. Because this is a reflection assignment. This reflection assignment asks you to first solve all of the problems on the test. This means even if you got it right, to redo the problem in its entirety. I want you to think about what you did wrong and what you did right. And for each problem, I want you to write down what went wrong. I also want you to write down something that you were proud of that you did. I want you guys to be a little bit positive, support yourself, and consider the things that you did well. I'm also asking you to reflect on sort of your study habits up until the exam. What did you do? What do you think worked? What do you think didn't work? And take some time to create a goal for the next test that you have, and to also give some advice to a student who will be taking this test next year. So that is your reflection assignment. If you do all of this and turn it in to me, then you will receive back a substantial amount of points depending on how you did on the test. You're going to receive back half of the missed points if you do it and you do it thoughtfully and thoroughly. So this does mean you're not giving me one-sentence responses, you're giving me full responses. So take your time on this. It's a chance to earn back some points. All right, I'm going to start calling out names. If you hear your name, come up and grab your test. Once you have your test, you are free to head out. Are there any questions before I do that? Yes, in the back. There was one from last time. You should have one blue card. Okay. Nesma.